Welcome back. Today we're going to look at complex numbers. This could be a long section, so if it ends up being 2 videos, please look for that second video. That's a distinct possibility. Alright, complex numbers. We know what real numbers are. Real numbers are things that we use in everyday life. There's a lot of properties in mathematics that require a new set of numbers to be created. Okay? And those numbers are called complex numbers. Now, what we saw a couple sections ago is sometimes your graph does not cross the x-intercept. Okay? It doesn't cross the x-axis. So what that means back then was that there was no real solution. Well, we looked at the fundamental theorem of algebra that said the number of solutions must match the degree. So if we had an x squared problem, there had to be 2 solutions. If we had an x cubed problem, there had to be 3 solutions. Well, what that means is those extra zeros are what are called complex numbers. And the complex form, standard form, is a plus bi. So we've got this idea of I here, and that is your imaginary numbers. So in this section we're going to be looking at imaginary numbers. Well, here's what imaginary numbers are. Imaginary numbers exist when you have the square root of -1. And if you tried in your calculator to take the square root of a negative number, you couldn't do it. And the reason is a perfect square is when 2 numbers get multiplied together to make a larger number. Well, they have to be the exact same number. So if I took 4 times 4, I would get 16. If I took a -4 times a -4, I would get 16. There's no possible way to multiply the same number together and get a negative. I would have to have -4 times +4 to get that -16, and that is not a perfect square because 4 and -4 are not the same numbers. Okay, so it's impossible in the real numbers to multiply 2 things together that are the same and get a negative. That's why you can't take a negative square root. So this negative square root gives us this I value. Now, one important property is the one right here on the right hand side. I squared equals 1. So if I were to square the I and square the square root, your square and your square root would cancel, and that proves that I squared equals -1. Now this property gets used quite a bit. Just keep that in mind. So I squared, whenever you see that, is going to be substituted with a -1. Alright, our first set of examples asks us to simplify. Now, when you simplify these, you treat them very similar to regular square roots. Okay, now what's going to happen is you can break these things apart. So the square root of a -16, I can turn it into the square root of +16 times the square root of a -1. Well, we know what the square root of 16 is. The square root of 16 is 4. Now the square root of -1, we just saw that property. It's right here. The square root of -1 is an I. So anytime you have that negative, you're going to get an I. So this becomes 4i, and that's your final problem. Alright, for B, you've got the square root of 24. Well, the square root of 24 could be written as the square root of 24 times the square root of -1. Well, there is no perfect square for 24. However, there is a perfect square that goes into 24, and you should have this knowledge already. So I take 24 and I break it down to 4 times 6. I take my -1 and leave it there. So the square root of 4 is 2. That's gone. The square root of -1 is I. That's gone. The square root of 6 can't be broken down, so it's left as the square root of 6, and that is now your final answer. Okay, quickly, pause the video, try C, come back and see how you did. Okay, for C, if you break this apart, the square root of 200. Well, I know that 100 goes into 200, and that is a perfect square, so that's a great place to start. That would leave me with a 2, because 2 times 100 is 200, but I also have that negative in there, so I've got the -1. So that's now broken apart. Square root of 100 is 10. Square root of -1 is I. Square root of 2, can't do anything with it, so I put it on the end, and there's your final solution. Alright, so that's how these imaginaries work. It takes some getting used to, but treat them like normal square roots. The only difference is when you have that negative underneath, an I value will come out. Now what we can do with this is treat these just like real numbers. Okay, real numbers can be multiplied, so can imaginaries. Okay, so if I take this first example, -5i times 3i. If that was -5x times 3x, you can multiply that together with no issues. It's the same thing here. So I take my negative 5 and my 3, and I get a negative 15. Now I times I is just I squared. Now remember up above, I told you we have a property that we're going to use. It's I squared is negative 1. Every time you see an I squared, you're going to replace that with a negative 1. Okay, so I've got a negative 15 times a negative 1. That just works out to be 15, and there's your final solution. Okay, so watch that. Just be aware, be careful. Alright, the next one. I've got the square root of negative 6 times the square root of 15. Well, with this, I cannot do anything with those negatives underneath, so I've got to pull them out. So for each of these, those negatives right there and right there, give me an I. So this turns into I square roots of 6 times I square roots of 15. Okay, now I can multiply these things. So when I multiply, I get I times I, which is I squared. We've seen that, we know what happens. Okay, then you have 6 times 15. 6 times 15 is 90. Well, 90 is something that can be broken down. That is 9 times 10. And when I take the square root of each of those, the 9 gives me a 3. The 10 has to stay under the square root of 10. But what about this I squared? Well, remember, I squared is a negative 1. And if we multiply 3 square roots of 10 times that I squared, or the negative 1, you end up with a negative 3 square roots of 10, and there's your solution. Now the last possibility is binomials. And if we have binomials and you had this with the variable, what you'd end up doing is foiling. And it works the same way. We're still going to FOIL. So we go 3 times 5, 3 times negative 3i. 2i times 5, 2i times a negative 3i. Okay, and see what happens. So 3 times 5 gives you 15. 3 times a negative 3i is a negative 9i. You've got a 2i times 5, so that's a 10i. And then a 2i times a negative 3, which is a negative 6i squared. Well, from a property we've seen, we know that this I squared turns into a negative 1. So if I rewrite that with that fact, and I'm going to hold off in just a second for combining like terms, the negative 6 and the negative 1 turn into a positive 6. And so it's just going to change that sign. That's what an I squared does. It becomes a negative 1, changes the sign. And now I have some like terms. So I have a 15 and a 6, that's 21. You have a negative 9i and a positive 10i, that's positive I. There's your solution, and you're done. So treat these just like real numbers, with the exception of if you end up with an I squared or a negative underneath that square root. Now what this does is it leads to us to be able to solve solutions. Okay, this is where if our graph does not cross the x-axis, we can still get a solution. Alright, here's how it works. We've talked about before there is no such thing as sum of squares. Okay, there's a difference in squares, no sum of squares. So you get a problem like this, eventually, or previously we wouldn't be able to solve it. Now we can use these square roots. To use the square root property, you get the square root by itself. So you subtract 64 from both sides, you got a negative 64 over there. Now what we want to do is take the square root. If I square root both sides, the square and the square root cancel, and that gives you an x. On the right hand side, you've got the square root of a negative 64. We know how to deal with that now. The 64 becomes 8, the negative becomes I, and since we're solving equations, we have to take into account the possibility of a positive or negative, so it's x equals plus and minus 8i, and there's your solution. Okay, so move it to get the x by itself, take that square root, and then just simplify. Alright, on your own, pause the video, give yourself a minute or two, and try example B. Alright, welcome back. Hopefully you guys were able to work through this. To get this x squared by itself, we're going to first start by subtracting 100. So I subtract 100 from both sides to end up with something that looks like this. Now I'm going to divide by 4. Okay, so that gives you x squared equals a negative 25. Now once we've got that x squared, we know that we need to take the square root. So you end up with x equals, the square root leads us to a plus and minus, and then the square root of a negative 25 is a 5 for the 25, an I because of the negative, and there is your final solution. All right, let's keep plugging along. Now, addition and subtraction. Addition and subtraction gets to be very simple if you pay attention and are careful. Now, with these complex numbers, you have two parts. You have the real part, which is the A, and the imaginary part, which is the BI. And for addition and subtraction, you can only combine similar parts. So we look at our first example here. You got 5 minus 7i plus 2 plus 4i. Well, ask yourself, what are the real parts? The real parts are 5 and 2. They don't have the imaginary number with them. So you can combine those using the operation. In this case, it's addition. So you go 5 plus 2, that gives you 7. Okay, then you look at the imaginaries. We have two imaginaries. We have a negative 7i, we have a positive 4i. And we're going to add those together. So it's a negative 7i plus 4i, that gives you a negative 3i, and there's your solution. You're done. Okay, now just be careful to watch your signs, make sure you know what they're asking you to do. Now for subtraction, it's the same idea, but be careful with the signs. There's a lot of mistakes that occur with those signs. So real parts are 4 and 3, and they're asking you to subtract. So it's 4 minus 3, which is 1. Then you take your imaginaries, which is negative 8i, negative 6i, and we're subtracting them. And again, watch your signs. So it's negative 8i minus a negative 6i. So the minus and negative, because of multiplication, negative times negative is a positive. So negative 8i plus 6i gives you a negative 2i, and there's your solution. So that is the addition and subtraction of these imaginaries. Okay, to finish this up, last thing here is complex conjugates. Now conjugates are numbers that are of this form, a plus bi, a minus bi. They're different in that that sign in the middle is different, and that's the only thing. Now the reason we have to use these is we cannot leave an imaginary number in the denominator of a fraction. Right? So if you look at our first example here, you've got this 6i in the denominator. That's not allowed. So we want to find a quotient. We got to multiply by the conjugate. So the conjugate of 3 plus 6i would be 3 minus 6i. Now you have to do it in the numerator and denominator because 3 minus 6i over 3 minus 6i is 1. And you can multiply anything by 1 and it stays the same. So now when you multiply, you just distribute. So 2i times 3 is 6i. 2i times a negative 6i is a negative 12i squared. And we'll deal with that in a second. Now in your denominator, you're going to end up foiling. Okay, so when you FOIL this, you get 3 times 3, which is 9. 3 times a negative 6i, which is a negative 18i. 6i times 3, which is a positive 18i. And then 6i times a negative 6i, which is a negative 36i squared. Now from this point, we're going to start simplifying a little bit. In your numerator, you've got this I squared. We saw that before. That becomes a negative 1. So you've got a negative 12 times a negative 12, or sorry, negative 12 times a negative 1, which is a positive 12. And then your 6i goes on the end. In your denominator, what will happen every time is those two things will cancel out. The i's drop out of the problem. This I squared becomes a negative 1, and so that whole thing right there becomes a positive 36. So you've got a 9 plus 36, which is 45. And the last step, if possible, is to see if you can reduce. So between 12, 45, and 6, it must be all three. Is there anything that goes into all of them? And the answer is yes, 3 does. So we're going to divide all of them by 3. Okay, so 12 divided by 3 is 4. 6i divided by 3 is 2i. And 45 divided by 3 is 15. That is now your final solution. Notice there is no more I in the denominator. That's how we know we're done. Alright, for B, this one can be done the same way, but it's even got a little bit of an easier step. I want to get rid of this I in the denominator. We know that I times I is I squared, or negative 1. So I could even just multiply by an I. And when I distribute this, so you go 4 times I and then I times I, you get 4I plus I squared. In your denominator, you get 5I squared. Now I want you to be careful and understand the I squareds cannot just cancel. Okay, you have to simplify. Well, that is negative 1. So in the numerator, you get negative 1 plus 4I. And I'm writing it with my real number first because that's standard form. 4I minus 1 is still okay. It's the same solution. But we want to try and put things in standard form. In the denominator, this I squared is negative 1. So 5 times negative 1 is a negative 5. And you get that. Now that's an acceptable answer. And again, in math, we've got these rules. We prefer not to have a negative in the denominator. So the last step would be to take this entire thing and multiply by negative 1 over negative 1, just to eliminate those negatives in the denominator. You get 1 minus 4I over positive 5. There's your final solution, and you can be done. But the one above in the blue is acceptable. It's essentially the same thing. Okay, those are complex numbers. They're a little different, I understand that. If you need some extra help, please contact me online. I'll work through this with you. And good luck on your assignment. We'll talk to you soon.